Hello and welcome. In this video, we will discuss the addition reactions of hydrogen halides to double bonds, its mechanism, and we will also be giving special emphasis to Markovnikov's rule and peroxide effect. So, we have already seen that addition reactions are initiated by electrophiles and therefore they are referred to as electrophilic addition reactions. Here, we will be dealing with the addition of hydrogen halides to alkenes. Again, they are electrophilic addition reactions. We can represent the reaction as shown. This is a double bonded system and to which the hydrogen halide is to be added. And we can see that hydrogen is added to one of the doubly bonded carbon atom and halogen to the other carbon atom. And therefore, we will get an addition product. But here, the hydrogen halide, it undergoes ionization to give H plus and halide ions. Here, H plus is the electrophile and X minus, that is counter ion, is the nucleophile. However, the reaction will be initiated by the electrophile and hence it is an electrophilic addition reaction. Now we will see the addition of hydrogen halides to alkene. Here we are actually dealing with an example, that is addition of hydrogen bromide to ethylene. Hydrogen bromide will be added to ethylene to give bromoethane, one bromoethane. That is hydrogen will be added to one carbon atom, one of the doubly bonded carbon atom, and bromine to the other to give the additional product. But here the reaction takes place like this. HBr undergo ionization to give H plus and Br minus, and H plus is the electrophile here that will be added to the ethylene molecule to give a carbocation, and this carbocation will be attacked by the nucleophile Br minus to give the additional product. Another example is the addition of HBr to propene. Here our substrate is 1-propene and it is reacted with HBr. So it will undergo addition reaction. But in viewing the reaction as explained in the last slide, we should get two products, namely A and B. If hydrogen is added to the terminal carbon atom and bromine to the next carbon atom, then we will be getting 2-bromopropane, that is compound B. And if hydrogen is added to the second carbon, that is carbon atom next to the terminal, and bromine or bromide to the terminal carbon atom, then we will be getting compound A, 1-bromopropane. So the addition of HBr to propene can generate two products, namely 1-bromopropane and 2-bromopropane. Now the question arises, which compound, A or B, which predominates here? That we will see from the coming slides. We will see the mechanism of the reaction. Hydrogen halides, they add to the double bond in a three-step mechanism. By a three-step mechanism, the addition follows a three-step mechanism. In the step 1, there is a generation of electrophile, and that is by the ionization of the hydrogen halide. And the second step, a carbocation is generated by the addition of the electrophile to the carbon-carbon double bond center. And in the third step, the nucleophile will be added to the carbocation to give the addition product. Now we will see each step in detail. In step 1, the generation of the electrophile. See, the electrophile is generated by the ionization of hydrogen halide. We will get H plus and halide ion. Here H plus is the electrophile. This electrophile will take part in the next step because the reaction is triggered or the reaction is initiated by the electrophile. In step 2, this electrophile formed in step 1 it will be added to the carbon-carbon double bond to give a carbocation. But here, the question arises, to which carbon atom the H plus adds? It can add either to the terminal carbon atom or to the next carbon atom, to the terminal carbon atom. So if H plus adds to the terminal carbon atom, then we will be getting a secondary carbocation. If hydrogen atom is added to the second carbon atom from the terminal position, then we will be getting a primary carbocation. But it should be noted that the secondary carbocation is a more stable carbocation, and therefore we expect the reaction to proceed with this structure, that is with the secondary carbocation. Now the carbocation formed in step 2, it can undergo the following rearrangements or the following reactions. Whenever and wherever a carbocation is formed, it can undergo either elimination or rearrangement or attack by a nucleophile. That is, a carbocation can be stabilized by these three ways. When a carbocation is formed, it can undergo beta elimination to give an alkene that we have already discussed in the case of elimination reaction. And when a carbocation is formed, it can undergo rearrangement to give a more stable carbocation. That is, if somewhere a primary carbocation is formed and if the carbocation finds some chance to rearrange to a tertiary or a secondary, then that will opt for that rearrangement. If there is an option for a tertiary generation of a tertiary carbocation, then the carbocation will rearrange to give a tertiary carbocation. And if there is only a scope for secondary, then the primary carbocation will be rearranged to a secondary carbocation. And the third option is that the carbocation is attacked by a nucleophile to give the addition product. These are the three options for a carbocation. So whenever and wherever a carbocation is formed, it can undergo any of these three reactions. And here we encounter the third one, that is the carbocation will be attacked by a nucleophile. So in step 3, the nucleophile, that is a counter ion, the halide ion, it will be added to the carbonium ion or the carbocation to give the addition product. Now we will see the mechanism of addition of HBr to propene. Here in the step 1, HBr ionizes is to give H plus and Br minus, and H plus is the electrophile here. This electrophile will be added to the alkene, that is 1-propene, to give a primary carbocation or a secondary carbocation. There are two chances. But the secondary carbocation being more stable, the hydrogen atom will be attacked to the terminal carbon atom to give the secondary carbocation, and the reaction proceeds with this structure, that is with the secondary carbocation in the third step. In the third step, the secondary carbocation will be attacked by the Br minus to give the addition product, and therefore the addition compound formed here is 2-bromopropane. Thus, we can find that the reaction proceeds with the most stable carbocation. And this supports the observation that was made by a scientist called Markovnikov in 1869 when he studied the addition of HBr to an alene system in 1869. He found that he arrived at a statement. He arrived at a statement that in the addition of an unsymmetrical reagent to an unsymmetrical alkene, the negative part of the addendum is added to that carbon atom containing the least number of hydrogen atoms. So this we will see the Markovnikov's and this statement is called the Markovnikov statement or the Markovnikov's rule. And this we will see as an example. See, this is an unsymmetrical reagent. Hydrogen bromide is an unsymmetrical reagent, and 1-propene is an unsymmetrical alkene. unsymmetrical alkene in the sense that you cannot cut this alkene into two equal parts. But on the other hand, if you go for ethylene molecule, that could be, ethylene could be cut into two pieces, two exact pieces. Therefore, we say that ethylene is a symmetrical alkene, while propene is an unsymmetrical alkene. So the Markovnikov's rule sounds only with the unsymmetrical alkene. So in the addition of an unsymmetrical reagent to an unsymmetrical alkene, the rule states that the negative part of the addendum, here the addendum is HBr and the negative part of the HBr is Br, that will be added to that carbon atom, that doubly bonded carbon atom containing least number of hydrogens. And therefore, H plus should, the positive part should automatically go to the other carbon atom. And therefore, Markovnikov's rule says that when one propene adds with, when one propene reacts with HBr, we get actually 2-bromo propane. This is actually what the reaction mechanism also says. Next, we will see the addition of hydrogen bromide to propene in the presence of a peroxide. And this is known as a peroxide effect or Karash effect. And this observation was made by a scientist, Morris S. Karash, in 1933. That he observed that in the addition reaction of HBr to propene, when the reaction was carried out in the presence of a peroxide, then instead of 2-bromopropane, we are getting 1-bromopropane. That is, anti-Markovnikov's products are obtained when the reaction is carried out in the presence of a peroxide. So peroxide plays a role here. This is the situation. 1-propene, it reacts with the bromine in the presence of, 1-propene reacts with the hydrogen bromide. In the absence of any peroxide, we will get the Markovnikov's product, namely 2-bromopropane. And in the presence of peroxide, we get 1-bromopropane, which is the anti-Markovnikov's product. Now we will see the reaction mechanism. Actually, here the reaction mechanism is actually a free radical addition mechanism. Free radicals, as you know, they are those chemical species containing odd unpaired electron. At least one odd unpaired electron species are termed as free radicals. These free radicals are still electrophiles. Therefore, still the reaction is electrophilic addition reaction. But to be specific, we will say that it has a free radical addition mechanism. Free radicals are always electrophiles. Step 1. Here we can see that a peroxide take part. Peroxide decomposes to give free radicals. This is the peroxide linkage. Oxygen-oxygen linkage is otherwise known as a peroxide linkage. This peroxide linkage is susceptible to homolysis to give free radicals. So this is an alkoxide free radical. In the step 2, the free radicals formed in the step 1 will react with HBr. That is, they will abstract a hydrogen from HBr to generate a bromine radical. Bromine radical is same as bromine atom because it contains odd unpaired electron. Now, this bromine free radical attacks propene. See, the reaction is represented here. Bromine free radical can attack at this carbon-carbon double bond because a Br dot or bromine free radical being electrophile, it will add towards the carbon-carbon double bonded center. And here we have two options. Either bromine free radical can attack at the terminal carbon atom or to that carbon atom next to the terminal carbon atom. And those two are doubly bonded. So we will get primary or secondary. But actually we will get secondary. The reason is that secondary free radicals are more stable than primary. So that is, it should be noted that the order of stability of free radicals, the order is given by primary is the least stable and tertiary is the most stable. So in the case of addition of bromine free radical to one propene, we will get a secondary free radical, and therefore the reaction proceeds with this secondary free radicals because they are more stable. And in the fourth step, the secondary free radical, it abstracts a hydrogen radical from HBr to give the anti-Markovnik's product. So HBr, hydrogen is abstracted. Here H will be added to hydrogen atom will be added to this carbon atom next to the terminal carbon atom, and therefore we will get anti-Markovnik's product, and bromine free radical will be again generated here that will be used for the next cycle of the reaction. So it should be noted that the peroxide effect follows a free radical mechanism, and therefore the anti-Markovnik's products are obtained only if the reaction follows a free radical mechanism. Therefore, the condition is that our substrate should be capable of producing free radicals. Otherwise, the reaction won't happen. So if you take a series of hydrogen halides, say HF, HCl, HBr, and HI, then only HBr is capable of producing a free radical. That is, a bromine free radical is a best free radical form. However, HF and HCl, they are not capable of producing free radicals. However, HI can give rise to free radicals, but iodine free radicals are least reactive. They will undergo recombination. Therefore, the best substrate for the free radical mechanism study in the case of addition reaction to alkene is HBr, hydrogen bromide. And the peroxide effect is therefore not observed with HF, HCl, and HI. And it is observed only with HBr. Thank you.